The Diels-Alder reaction is a cycloaddition reaction. So we're going to take two molecules and we're going to add them to each other so that they form a ring. So we're adding them to form a ring, so it's cycloaddition. And it happens between two very specific types of molecules. The first one is called a diene. This is a molecule that has two conjugated pi bonds. So one here, notice double, then single, then double. So it's alternating, so it's conjugated. And you have another pi bond here. That's one molecule in the Diels-Alder reaction. The other one is called a Dienophile, and that's usually just something that has a double bond in it. To predict the product that you'd get, draw a dotted line between the ends of the diene and the ends of the Dienophile, and then use curved arrows to move all of the pi electrons in the same direction. So here, they're all going clockwise. Move them over clockwise. So these pi bonds will form a sigma bond, these pi bonds will form a sigma bond, and this pi bond will move over to form a pi bond in a new place. So you formed this bond, and the pi bond that was down here moved over. Now we're going to talk about all this in a little bit more detail and why it's happening. It should look really strange because you don't have any positive or negative charge in these molecules. So it's not that opposite charges are attracting here. That's not the cause of this reaction. So if we go back to figure out what the cause is, if we go back and we think about the two pieces that we're working with here, we want to look at those pieces and think about the molecular orbitals that are on each of these pieces. So let's start with this piece on the left. We have two conjugated pi bonds. That means we have 1, 2, 3, 4 p orbitals. Anytime you have a pi bond, you have parallel p orbitals on the two carbons in the pi bond. So you have 1, 2 there, 1, 2 there. So we have 4 parallel p orbitals in this conjugated system. And those and that means that the electrons in those p orbitals can move around all 4 of these atoms. So when electrons move, they always move as waves. And what type of a wave they move in depends on how energetic they are. The lowest type of wave, the lowest energy type of wave that they can move in is just all going up or all going down. So here they're all in phase. Imagine plucking a guitar string and the guitar string either goes completely up or completely down. That would give you the lowest note, the lowest energy for the way that that wave could move. But if you pluck the guitar string and now half of it goes up and then it goes down, half of it goes up and then it goes down, that will give you a higher note, and so you'd have a higher energy. And you can notice that the more of these nodes you have, where the phase switches from going up to going down, the more of those nodes you have, the more waves you're fitting in the same space, and so the more energetic those waves are. So these waves are going over the whole molecule, so they're called molecular waves. But the technical term for a wave, when the wave that an electron is moving in, is an orbital. So these are molecular waves, but they're for the way electrons move, so they're called molecular orbitals. And when they move even faster, then you get even more nodes. The nodes are always symmetrical. So here you have 2 nodes, and the only way you can have that symmetrically is like this, and then even faster you have 3 nodes. So these are all molecular orbitals from the lowest energy wave that the electrons can move in over these 4 carbons to the highest. Now, the only electrons that can move in this are the ones that were in the p orbitals. We have 2 electrons in p orbitals from the top pi bond, and 2 electrons in p orbitals from the bottom. So that's a total of 4 pi electrons that we have. Only 2 electrons can fit in each of these waves because the electrons are like little magnets. You could have the north side pointing up or down. But once you have both of those arrangements, if you try to stuff another electron in there, the new electron will either be a little magnet pointing up, in which case the one that's already pointing up will repel it, or it'll point down, in which case the one that's already pointing down will repel it. So you can't fit more than 2 electrons in any of these waves. So once this way of moving, this wave pattern, is filled with 2 electrons, the next 2 electrons have to start moving in a different wave, and so they move in this more energetic wave. And so the takeaway you want to have from this is that this orbital right here is occupied. The bottom two orbitals are occupied. The top one, this Psi2, that's the highest occupied molecular orbital, and it has an abbreviation called the HOMO. So it's the highest occupied molecular orbital, and notice it just has one node in the middle. That's going to be important for this reaction. So you'd see those abbreviations. The HOMO is the highest occupied molecular orbital, and then the next one up is unoccupied. It's called the lowest unoccupied molecular orbital. So this is a way that electrons could move, but they're not moving in this molecule, so it's called the LUMO. Now, the other character in our drama is our Dienophile, the double bond. And here there are only two ways that the wave patterns that the electron can move in. Either the two p orbitals are in phase, so it's like that lowest energy of the string that you pluck. Either the whole string goes up or the whole string goes down, and it gives you a low energy note. Or it goes up and down, up and down. So the phase shifts. It starts out down, then it shifts where the node is, and it goes up. And that's the higher energy way that a wave can move in this smaller space. So here we have only two pi electrons moving in these p orbitals, and at the lowest energy, that lowest energy wave fills that here. So that bottom one is called the HOMO, the highest occupied molecular orbital for this Dienophile, and the one right above it is called the LUMO, the lowest unoccupied molecular orbital for the Dienophile. Now notice, in the conjugated system, the lowest energy wave is lower in energy than in the Dienophile. This Dienophile, the energy is going up. You have to get higher energy in order to have electrons fly like this. And that's because in this Diene, the electrons are more spread out. In this case, the electrons are able to spread out over 4 carbons, whereas in the molecule on the right, they're only able to spread out over 2. And there's a big important principle that unifies a lot of things in organic chemistry, and that's that the more charge spreads out, the more stable it is. And another word for stable is low in energy. So here we have this low in energy. Then we have this next orbital that's higher in energy. And then we have this next orbital that's higher in energy. And then we have this LUMO. Now notice, we have a lot of electrons. We have more electrons in the Diene. Those electrons would love to spread out, if they could, in the closest energy thing that's nearby. The closest way that electrons can move if these two molecules knock into each other is in this LUMO. So what can happen is, if these two molecules knock into each other, the electrons in the highest occupied molecular orbital of the Diene can bleed in to the empty, lowest unoccupied molecular orbitals of the Dienophile. So to help you visualize that, you can view this next demonstration. So the Diels-Alder reaction is a drama that happens between two characters. The first character is the Diene, 2 conjugated pi bonds. And it's the highest occupied molecular orbital of the Diene that interacts to create the reaction. The highest occupied molecular orbital of the Diene looks like this. So you have the one node right in the middle where the wave pattern switches. So these are 3-dimensional standing waves. In a 2-dimensional wave, the wave goes up and down. Whenever the wave goes up, they represent that by one color, and if that's going up on one side, it's going down on the other. They represent that by another color. So those waves are switching in that node right in the middle, where it goes from blue on the top to red on the top. And this is the highest occupied molecular orbital for the Diene. So that's one character. The other character is called the Dienophile. So this is usually just something that has one double bond. So you'd have your first bond represented by this beautiful balloon there, and then your second bond is going to be represented by 2 parallel p orbitals. But those have both a highest occupied molecular orbital, and then they have this one. This is the lowest unoccupied molecular orbital for the Diene. So this one needs electrons. This is a way that electrons could move around this molecule, but they're not there right now. And in our other molecule, we have the highest occupied molecular orbital. This has so many electrons that are just itching to spread out in space. And so when you take these two molecules, the Diene on top and the Dienophile on the bottom, these wave patterns come together so that the blue phase on one side matches in the Diene and the Dienophile, and the red side matches on the other side of the Diene and the Dienophile. And those two waves overlapping is what creates a new bond between the molecules. So when these two blue waves overlap, it creates a single bond there that didn't exist before. When the two red waves overlap, it creates a single bond there that didn't exist before. And so you end up getting a ring that you didn't have before. So it's really significant, both because you're making two new carbon-to-carbon bonds. Organic chemistry is the chemistry of carbon. And when you can make new carbon-to-carbon bonds, you're able to make shapes that now fit into pockets that they didn't fit into before. You're able to make two new carbon-to-carbon bonds, and you're able to make a ring, which is really significant because rings have a rigid shape, so they reliably fit into receptor sites. Whereas with straight chains, the bonds can rotate all the time. So they're like a soft piece of spaghetti in boiling water. Their shape is constantly shifting. So in the Diels-Alder reaction, you have a Diene, a Dienophile, and you're creating two new bonds, not because you have any type of charge, not because you have a nucleophile and an electrophile, but because the phases of the molecular orbitals are overlapping in the system. So just for fun, I want you to see how the molecular orbitals change as the reaction happens. So on top we have the highest occupied molecular orbital for the Diene. So we have that one phase on the left, you have the node in the middle, and then the other phase on the right. And then we have the lowest unoccupied molecular orbital for the Dienophile down here. So these are all pi bonds. When they go together, when they move together, you can see how at the end you end up with two sigma bonds. So these are sp3 orbitals here overlapping and the small end of the sp3 orbitals pointing in the opposite direction. So those are single bonds. And then you still have that pi bond, but it's moved over now on the top. So you could see how those molecular orbitals change just because it's so fun and beautiful. Let's see that one more time. And just so you can visualize what's happening in terms of the molecular structure in 3D, let's view this animation. So here we have our Diene, our Dienophile. An electron withdrawing group is attached. Remember, we're using the lowest unoccupied molecular orbital here. If we attach really electronegative atoms, then that's going to steal even more electron density there, and it's going to be even lower in energy. This is going to want electrons even more. Right? So remember, these electrons are feeding into this orbital. The electrons in the highest occupied molecular orbital here is feeding into the lowest unoccupied molecular orbital here. And so this is going to want to eat up those electrons even more if you attach an electron withdrawing group that steals even more electron density from it. But you have that there, and then you just draw those curved arrows to show it all going in the same direction. So here they're all going clockwise to show how you produce that new ring. So to see how that happens in 3 dimensions, you can view this. Now we'll view this from 2 sides. So just kind of viewing it on top, you see the new 2 sigma bonds form and the new pi bond forming. And if you wanted to view it from the side, that same reaction would look like this. And there you have the Diels-Alder reaction.